Well, good morning, everyone, or good afternoon, as the case may be. This is David Castor with EasyPower, and we're going to spend a little time here today talking about some issues with protective device coordination. And these are issues that come up during training and tech support, so we thought we'd try to cover those, and we're going to do it using EasyPower. I'll be kind of jumping back and forth between some PowerPoint slides and my EasyPower model. So if you were hoping for a polished presentation, you'll probably be a little bit disappointed, but we'll hopefully have some time at the end for questions. This is my first time using the webinar software, so I think right now the audio for the participants is muted. I think you have a way to raise your hand or flag if you have a question, and then we can unmute you, or you can ask your question. And so if I don't get to all the questions, or if I don't get them in the right order, then that'll be on me, but hopefully we'll get better at this the next time. So I'm going to go ahead and get started here. I think we got probably most of the people are here. So we're going to talk about a few kind of random topics. First one is molded case circuit breakers versus low voltage power circuit breakers. And that question comes up a lot, and as far as why you would use one over the other and what the advantages are. We're going to focus mainly on coordination issues, but also we'll talk a little bit about short circuit duties. We'll talk about coordination of molded case circuit breakers, or the lack of coordination at times. That's become a bigger issue now because of some of the new requirements in the National Electrical Code. We'll talk a little bit about transformer damage curves. I know we get questions about that, and why is EasyPower showing two curves, and sometimes, but other times it doesn't. So we'll go through the basis for the damage curves and why things show up the way they do in EasyPower. And we'll kind of roll that into a more general discussion of transformer protection. We'll talk a little bit about the time current curves, what we call the clipping of the TCCs and the tick marks, which are the short circuit currents, as far as why those are there, why you would want to, what you would use those for, and how EasyPower works, and what your options are for changing that behavior. And then lastly, the question comes up a lot in the training about the I2t settings for the low voltage trip units, both molded case breakers and low voltage power circuit breakers. So we will discuss that a little bit at the end, and hopefully have some time for questions as we go. All right, so first topic is molded case circuit breakers versus low voltage power circuit breakers. We'll see in a minute here in EasyPower, when you enter a low voltage breaker, we use the same symbol for both these devices, but you need to select which category the breaker is before you start selecting manufacturer and style and all that, because they're two completely separate entities in the EasyPower library. And these devices are built to different standards. Molded case circuit breakers and insulated case circuit breakers are built to a UL 489 standard, and low voltage power circuit breakers are built to UL 1066, which in essence references several standards in ANSI C37. So in general, molded case circuit breakers are going to go in what we call switchboards that can either be group mounted or individually mounted. And the switchboards themselves are built to different standards than the switch gear, which is where the low voltage power circuit breakers are typically installed. And normally the low voltage power circuit breakers are installed in draw-out switchgear. And that allows a much faster replacement, more flexibility, and more reliability. So I'm not sure if this is in your way, but I can move this over a little bit. So if we look at a comparison between molded case circuit breakers and low voltage power circuit breakers, there's a lot of differences, but these are probably the primary ones we're concerned about. One of the biggest issues is the maintenance aspect. And basically, a molded case circuit breaker has no user serviceable parts. In fact, if you take it apart, you've kind of lost your UL approval of that device. The low voltage power circuit breakers, on the other hand, can be inspected and maintained, and pretty much anything in it can be repaired or replaced, including the main power contacts, the arc chutes, and you can replace or upgrade the trip units, current sensors, and all that. So much different approach to maintenance. The other major difference, particularly interesting when we talk about coordination, is what is called the short time duty cycle. And for a low voltage power circuit breaker, it must be able to carry the rated fault current for two 30-cycle periods, half second each. So that's what's sometimes called the withstand rating for that breaker. So it can carry that for 30 cycles without tripping. Whereas the molded case circuit breaker has no such rating. It's not required to have a rating. The manufacturers can test it and can certify that it has a certain rating, but it's not required to have it per UL 489. So what that means is that the molded case circuit breaker must have at some point an instantaneous trip, whereas the low voltage power circuit breaker can be applied without an instantaneous trip up to its full short circuit rating. Another factor that makes a big difference in looking at the equipment duty and the short circuit rating is the way that these are tested. So, and it has to do with the power factor, which in EasyPower relates to the X over R ratio of the fault. So when we do the training classes, and we spend a lot of time talking about X over R ratios, and this is one of the reasons why it's important to have that accurately modeled. The molded case circuit breaker is tested at a power factor of up to 20%. The low voltage power circuit breaker is tested up to only 15%. So that the lower the power factor, the higher the X over R ratio. So the low voltage power circuit breaker is tested to a more severe standard than the molded case breaker. And I have a little short example that shows you why you might care about that. So even though both devices are rated on a symmetrical current basis, that rating only applies up to its test power factor, or down to its test power factor. So if your particular system results in a lower power factor, this is the power factor at the fault point, then you have to derate that device. And I have an example I'll show you in a minute of that. As far as instantaneous trip, that's a big element for us when we're talking about coordination. So as we said, the low voltage power circuit breaker is not required to have an instantaneous trip. It has to have either short time or instantaneous, but it does not have to have instantaneous. You can buy it with instantaneous, but it's not required. With the molded case circuit breaker, it will have at some fault current level an instantaneous trip. So the bigger and more rugged molded case breakers can have quite high short circuit ratings, and the instantaneous trip can be quite high, but there will be a instantaneous trip there somewhere. Even on trip units on molded case breakers where it looks like you've turned the instantaneous trip off, there still will be an override at some level of fault current that will kick in. As we said, the normal application in molded case circuit breakers is going to be things like switchboards. This is UL 891. Also, of course, panel boards, motor control centers, those types of devices. The low voltage power circuit breakers are applied typically in draw-out type switchgear. These are going to take significantly more space, and the switchgear requires front and back access, where you can buy the 40-volt switchboards that are front access only. So if you have space constraints, that using low voltage power circuit breakers can be a bit of an issue. Another difference is the continuous current rating. As most of you know, at least in the US, the molded case circuit breaker, if I buy a 100 amp breaker, it's rated to carry 80 amps on a continuous basis, with continuous defined as 3 hours or more. In certain situations, I can specify a 100% rated molded case breaker, but that's an option or an additional cost item that you can purchase in some applications. By contrast, a low voltage power circuit breaker is always 100% rated in every application, so that does make a difference. I should also mention that the short circuit tests are different for these two devices, that because of the expected application, the molded case circuit breaker is actually tested with, I believe, 4 feet of the rated, whatever the rated size cable would be for that device on the load side, and that's where the short circuit's applied. Whereas a low voltage power circuit breaker is tested with a bolted bus fault, basically, at the load terminals. So just that extra few feet of cable can make a pretty big difference in the amount of short circuit current that the device actually sees. All right. So I have just a quick short circuit example here. This is a short circuit report from EasyPower. It's not the equipment duty report. This is a half cycle short circuit report. So we have these equipment duties here, these 2 columns that show up, and probably you've looked at that and kind of said, oh, I don't know what that is, so I'm going to ignore it. What we're trying to do is provide information related to any necessary derating of these devices due to the X/R ratio. In this column, we have the calculated short circuit current. This is the half cycle momentary. In this case, it's 39,600 some amps. Over here, this value is the adjusted duty. So why do we have to adjust? So what we're saying is that for this particular fault on this sub 8A bus, we would have to use this value to compare against our circuit breaker rating. So why is that? It's because of the X/R ratio. Remember, we said that these are tested, low voltage power circuit breakers are tested at a power factor of 15%. But in this case, the actual power factor is 14.4%. So that's lower than the maximum or the minimum power factor test value. So because of that, we have to increase the amps slightly to compare against the circuit breaker rating. So we calculated 39,609. EasyPower is saying that's going to, what you really need to use is 39,890, just slightly higher, because I'm slightly below 15%. But down here we have the molded case circuit breakers, and these, we'll look at the over 20,000 amp value. And this is 42,129. This value is higher because the multi-case breaker's test power factor was 20%. So we've exceeded that by a greater amount with this X/R ratio. So the bottom line is I can have a low voltage power circuit breaker that's rated for 42,000 amps. On this bus, that would be okay. And I can have a 42,000 amp multi-case circuit breaker on this bus, and that would not quite be okay. You would be slightly over the adjusted fault duty. Okay. So remember, when we talk about breaker duties, the duty is what it sees on your system. The rating of the breaker is what's on its nameplate. So we've increased the duty to do an apples-to-apples comparison based on this X/R ratio. All right, so that's an impact, a difference between multi-case circuit breakers and low-voltage power circuit breakers. And that is why we provide this information in the short circuit report. If you ran an equipment duty report, you would see the same adjustment made as well. All right, let's get back to coordination since that's what we were supposed to be talking about. We talked earlier about the short time withstand rating that the low voltage power circuit breaker has, and that allows it to stay closed and allows equipment downstream of that to clear the fault before that breaker trips, which is what you want. That's coordination or selectivity. For the multi-case circuit breakers, I don't have that short time rating necessarily, so it has to have an instantaneous trip. And that's going to limit our ability to coordinate between multi-case circuit breakers in series, upstream and downstream. And we mentioned that the newer multi-case breakers may be tested for the short time withstand, but it's not a part of the standard at this point. So in general, when I have more than one multi-case circuit breaker in series, there's a very good risk that it's not going to coordinate. Those two devices are not going to coordinate for high current faults. And if we use low voltage power circuit breakers, we have a much better chance of providing better coordination. So let's look at a couple of examples in EasyPower. So I'm going to have to jump over here. So bear with me. So here's just a EasyPower model. I'm going to jump over here. I kind of rigged the deck here a little bit, but I've got this substation here is 1500 kVA, 480 volts, and it's equipped with low voltage power circuit breakers, GE, AKR, and these have some kind of I think microburst trip units. This substation I have configured to have multi-case circuit breakers. Both 2500 amp mains, feeders are roughly the same size. So it just gives us a way to compare the performance and the coordination between the low voltage power circuit breakers and the multi-case. So if I look, I think I have a TCC here. If I look at the substation with the multi-case circuit breakers, it looks like this. So basically we have our primary fuse, this orange guy. This is the transformer damage curves. We're going to talk about those in a minute. Here's my main breaker. So if you hover over these curves, you'll get a blow up. If your eyes are bad like mine, then this is helpful to be able to read these notes. This is my feeder breaker. This is my motor circuit protector. Up here is the overload. relay on the motor. And this is the starting curve for my 125 horsepower motor. Seems like I need to zoom out here a little bit. There we go. So down here, we'll see these two curves overlap in the instantaneous region. So if I have fault current that exceeds the pickup of this main breaker's instantaneous trip, then we can't really say for sure looking at this that these two are going to coordinate. So I may end up tripping the main breaker. I may have a fault down here in the MCC. I may trip this main rather than the feeder. So that's just a limitation of multi-case circuit breakers. Now, these have adjustable instantaneous trips, so I can increase this instantaneous. So the higher I go, the more likely they are to coordinate, right? Because if my fault current's down here in this level, then the feeder should trip before the main, because the main here is on its short time delay. But get this out of the way. If I increase this, eventually I get to the maximum value, the override. So I can't get rid of this little piece. So why does this stop here? Why is this so narrow? It's because it's hitting the maximum fault current. We're going to talk about TCC clipping in a minute, and maybe that'll be help make that more understandable. But basically, this is the high as I can set it. So I'm still going to have a small region here where these two will not coordinate. But by setting this as high as possible, then I improve my odds, because these are maximum fault currents out here, right? So a lot of my faults, particularly arcing faults, are going to be a lower fault magnitude. So for those, these are going to coordinate. However, this feeder is not going to coordinate probably with this motor circuit protector. Remember, just because this curve stops here doesn't mean it's gone. When I get out here, this device is still there, right? It's still going to trip. It's just hit the 0.01 where I'm starting my time current curve. But life starts before 0.01 when a fault occurs. So that's just, sometimes we have manufacturers' data that goes down to a lower value. Sometimes it stops at 0.01. So you can see, if you zoom out, you can see what that looks like. So if I have a fault down here in the motor starter and the motor, and the fault current's up in this region somewhere, there's a pretty good chance that these are not necessarily going to coordinate. You can't really, I wouldn't count on it. All right, so that's the multi-case circuit breaker. Let's look at the low voltage power circuit breaker case. Again, I have a TCC here already. So now we see a similar situation, but in this case, I have low voltage power circuit breakers for my main and my feeder that do not have instantaneous trip. This is the short time delay for the feeder. This is the long time band. This is the long time pickup. So by adjusting these two delays so that they don't touch, these two breakers, the main and the feeder, will coordinate completely for all ranges of fault current. So I don't have to worry about these two coordinating. They should fully coordinate, assuming they both work, for any fault that's going to occur on my system. And I can do this because these devices have a withstand rating. They have that 30 cycle. So that allows me to not have instantaneous. So like everything in life, there's usually positives and negatives to this. The positive side of doing this is I have very good coordination. So because this feeder is going to coordinate completely with this motor circuit protector, because it's always going to wait a tenth of a second. We have a little bit of an issue here with the fuse, but that's for very high values of fault. And we'll show you in a minute that maybe that's not as big a problem as it looks like. What's the downside of not having instantaneous? Well, it's slower clearing times, right? In this era right now, we're thinking about arc flash quite a bit. So if I do an arc flash calculation for this bus, I get 10.7 calories. So that's my trade-off. If I have instantaneous, it's going to be much less than that. So if I go into my edit temporary in EasyPower, I can turn on an instantaneous trip and we can see the difference in the arc flash downstream. I'll set it at 10. So I put my instantaneous trip in and now my arc flash went down to 3.2 calories. So the downside of that is some risk of not coordinating with all of your feeders in the motor control center. So it's a trade-off. But typically or historically, we have elected to not put instantaneous trip on these to improve coordination. One other thing that I should mention is that it's easy to go into EasyPower and turn this instantaneous on and off. In the real world, it may not be quite that simple. Traditionally, we specified trip units with the functions that we wanted. So typically that we called them LSIG, long time, short time, instantaneous, and ground. Or maybe it was LSI if it didn't have the ground, or LS for long time, short time. So if I bought a long time, short time instantaneous, there was no way to turn off the instantaneous on that trip unit. I had to replace the entire trip unit. And that's true of most of the older trip units that are out there. So most of the newer breakers probably have a switchable instantaneous, whereas you can turn them on or off in the field. But for older breakers, older trip units, I would not count on that. You need to verify. If you want to get rid of the instantaneous or put instantaneous in, it may involve replacing the trip unit. The other thing in arc flash now is that the newer breakers will have, even if they don't have an instantaneous function for their normal protection, they'll have a maintenance mode. So you can switch in the instantaneous. Like we just did there, if someone is doing work on that motor control center, we switch into maintenance mode, turn on that instantaneous, and it will reduce the arc flash. You know, we take the risk of not coordinating during maintenance to protect the workers. All right. Let me jump back over to my so as we've said, the short time withstand that you get with the low voltage power circuit breakers does improve coordination. But again, you need to buy the trip unit without instantaneous or specify one that's switchable on or off. And these will coordinate with your downstream molded case circuit breakers. By the way, I will make probably a PDF of this PowerPoint slides available to you at some point here after the webinar. And I suspect you'll get an email on that, or we'll just make it available on the website. So this will be available to you. So the normal coordination, we use the short time delay difference to coordinate between mains and feeders when we have low voltage power circuit breakers. You can also use the zone selective interlocking, ZSIs, with low voltage power circuit breakers, and that kind of gives you the best of both worlds. So there's almost an instantaneous trip for faults that are in the main breaker zone. So, and we can model that in EasyPower as well, and maybe we'll do another session on that, talk about that in the future. So the big advantage in terms of coordination is on the side of the low voltage power circuit breakers. Much more flexibility because of that short time withstand rating. All right, so the multi-case circuit breakers in series, in the general case, do not coordinate in the instantaneous region. Now, if I know I have a certain level of fault current, I may be able to adjust the instantaneous trip of the upstream device to coordinate a little bit better. So I'm going to go back to EasyPower as I figure out how to do it. And I think I have a time current curve here. Talk about this a little bit. It's a general case of this looks pretty messy, but we have a lot of overlap here depending on the setting between these two breakers. So the main and the tie do not, or the feeder do not coordinate well because I can't get rid of these instantaneous trips. And I have another example here, which is, I think, the same one we looked at before. So again, because of that, as I said before, if my fault current is down in this region somewhere, then these two will coordinate. It's only for the higher range of fault currents that these don't coordinate. So if I increase the setting, I'm improving my coordination, but it's still not perfect. There's still a risk for high current faults of these not coordinating. So there's just a, put these on the slide so you'd have them in the PowerPoint. So we'll talk a little bit about selective coordination of multi-case circuit breakers. That used to be kind of a oxymoron, but in 2005, I believe, the NEC finally adopted a requirement that emergency power systems will selectively coordinate with some caveats and restrictions. But this had been promoted by some fuse manufacturers for many, many code cycles and was finally approved. The fuse manufacturers had a vested interest because they knew by test that if you apply fuses within the proper ratio, 2 to 1 or greater, that the fuses will coordinate, even though it doesn't look like they will on the TCCs. So the multi-case circuit breaker manufacturers kind of got to work and did similar testing and provided additional documentation, retested breakers to get a more accurate representation of the performance of the breakers in the instantaneous region. So really with multi-case breakers, there's two main techniques. If you can set the upstream breaker up, set the instantaneous above the actual maximum fault current, then it will never trip on instantaneous, right? The other option is to use multi-case circuit breakers that are tested combinations and are shown by test to coordinate up to a certain fault current. The series coordination is only valid by test, and so we get test data from the manufacturers. So basically, you're limited to the same manufacturer for the upstream and downstream device. I don't think anybody's going to test a GE breaker upstream and any Cutler Hammer breaker downstream, as far as I know. We do try to track this in the library, and but again, we're limited to the data that we get from the vendor manufacturer. This is just a screenshot of what's in the library related to series coordination. So this is a square D type RG breaker. There's a tab called series coordination, and in there are a lot of breakers listed as downstream devices. And it says that up to, for a PG breaker, up to 1200 amps, a 1200 amp breaker is going to coordinate up to 35,000 amps of fault current. That's what this is saying. This is the max value of fault current in kiloamps that this breaker PG downstream will coordinate with the RG upstream. So that's by test, or at least that's from the data that we got from the manufacturer. So how do we use this in EasyPower? Well, let me go back. So I have I'm in coordination focus now. I'm just going to highlight these items here to create a TCC. I'm going to add on this breaker and this little guy. Now I'm going to plot this. So you'll see we have this line that shows up. This is that EasyPower recognizes that these two breakers are a combination that it has in its library for series coordination. So it's saying that per the manufacturer, this main breaker and this feeder will coordinate up to 35,000 amps when the 8B main instantaneous is off or max. So it's not going to be off, but if it's off, there's still going to be an override. But so this is how that information is presented, at least at this point in time, in EasyPower. It kind of helps you understand what information that we have been given from the manufacturer about this series coordination between the multi-case breakers. So how do we get this curve to show up? Well, if we go back to protected device coordination options, when I'm in coordination, I have options here. So down here, I have this box that says show series coordination table tick marks. So if I check this box, when I create that curve, it'll look to see if those two devices, those two multi-case circuit breakers, are listed in that table, and it will draw that line in there for you. So that's how we're dealing with this at this point. Okay, so I'm running a little long here. So again, that's just how you turn that option on or off in EasyPower. And it looks like that. Okay, so we're going to jump over to coordination time intervals. And that is really related more to protective relays. So when I have a low voltage breaker and its trip unit, the time current curves that we look at are, they have some width to them, right? There's a tolerance band in the curve. So as long as those curves do not touch each other, those two devices will coordinate, because the band that they show on the manufacturer's drawing is supposed to include all of the trip unit tolerances, the breaker operating time, and everything. So all we have to do is make sure that we say we can see daylight between those two curves. They should coordinate. The relay curves, it's different, because the relay curve is only related to the relay. And so we have to allow for some additional separation between the relay curves to account for the breaker clearing time, the relay error, CT error, and those kind of things. Traditionally, and that means electromechanical relays, we use somewhere between 0.3 to 0.4 seconds, depending on how pessimistic the engineer was. When we have multiple relays in series, this gets to be, so we have to have that 0.3 seconds, say, between each pair of relays. The more relays I have in series, the slower and slower that last relay is going to be. So this becomes a problem. It gets very slow by the time you get up to your main bus or your main breaker. So the coordination time interval, sometimes we abbreviate it CTI. It accounts for the following extra time that we need to allow. The breaker operating time, which is somewhere between 2 cycles and 8 cycles, depending on the breaker. In the old days, we had relay over travel, where the induction disc would continue to turn due to inertia after the fault went away. We had just relay error. No device is perfectly accurate. We have CT error. No current transformer is perfectly accurate. And we also have other auxiliary relays, such as lockout relays, that take some time to operate. So in terms of the 0.3 to 0.4 seconds, has anything changed? Well, we have now digital relays that are extremely accurate. They have no over travel. So we can probably reduce this coordination time interval, but you still have the same breaker operating time issue, and you still have CT error, and in the extreme case, you have CT saturation, and that's probably another webinar. But if you put all that together, and there's no hard and fast rules on this, there's no code, there's only some consensus within the industry of what values are appropriate. So here's my table. I'm coordinating between these two devices. Here's my upstream device and my downstream device. So if I have electromechanical relay upstream with electromechanical relay downstream, we're saying 0.3 seconds. My downstream device is a digital relay. We're going to reduce that to 0.25. Direct acting trips would be like a 480 volt breaker. And there, like I said, that breaker curve includes all of the tolerances for the breaker, for the downstream device. So we can crowd that a little bit more. If I have a digital relay upstream and downstream, then we're saying you could probably reduce that 0.3 down to something like 0.2. And again, that's going to depend a little bit on your breaker clearing time and just how much you feel like pushing that. So this becomes a judgment that the engineer has to make, but we think something less than 0.3 can certainly be used for digital relay, coordinating with digital relay. So in EasyPower, we can look at how we can check the coordination time interval. So here I have a couple of relays. If I want to look at what's the time interval between these two relays, so I mean I can kind of do it visually, but EasyPower gives us a tool to make that a little bit more accurate. So if I hold down the shift key and select the two relays, I have a difference calculator here. It'll tell me there's 0.913 seconds. So that should be plenty. I can drag this up and down to see what it is at different fault currents, but it'll always, when I put it in, it always comes in at the minimum separation between the two curves. So this difference calculator is how we allow you to check that coordination time interval between any two curves. The only trick is you need to select the two curves first, then pick the difference calculator. Okay. We're going to jump over to transformers and quickly go through the transformer protection. So we have three things kind of we're worried about with transformers, mainly at least current related events. Long-term overloads, internal transformer faults, and what we call through faults. So a through fault would be a fault that's on the other side of the secondary side of the transformer. So the problem there is the transformer has to supply the fault current, and it's usually current way in excess of its actual rating. So when we show the transformer damage curves in EasyPower, that only deals with through faults, not overloads, not internal faults. So I mean, if you have an internal fault, the transformer is already damaged, right? So that's kind of The damage curve is not really applicable in that case. So the damage curve is only for through faults. So this is a typical curve you'll see in EasyPower. There's two main pieces of this. This little line down here is what we call mechanical damage. That's the stresses that occur due to the magnetic forces on the windings. This curved line up here is the thermal damage portion of the curve. And again, this is only for through faults. So this is specified for oil field transformers in ANSI C57-109. We also have to take into account whether this transformer is going to be subjected to frequent or infrequent faults, and we'll talk about what that means. Uh-oh. We're back. Hope you're still there. If you look at ANSI C57-109, it's broken down into 4 categories. And there's size, based on size, kVA ratings. So for 3-phase transformers, category 1 goes up to 500 kVA, category 2 up to 5,000, 3 goes up to 30 MVA, and class 4 goes above 30 MVA. So we talked about frequent fault. This is the criteria in ANSI how they define frequent faults versus infrequent. So for this up to 5,000 kVA, they're saying 10 faults in the life of the transformer, 10 through faults, would be considered frequent faults. So you would want to use the frequent fault curve, which includes the mechanical damage. But for the larger transformers, it's a lower number. So it's 5 for the transformers above 5,000. So if I look at, go back to EasyPower here. Let me do this. If I'm still in coordination, I have my transformer. So if I just say plot TCC, I'm going to get my damage curves. So if I double click on this, I get my data for this transformer. I can edit this protection data. So down here we have a box called frequent fault curves. Right now it's checked. That's going to be the default. If I uncheck this, say apply, then this straightens out. So basically the frequent fault curve takes into account the mechanical stresses, the mechanical damage. When I go to the infrequent fault, I lose it doesn't take the mechanical damage into account. This is strictly the thermal curve. So the frequent fault is going to be more restrictive, so it's typically you would try to protect against the frequent fault if you can. And you know, if you get in a bind and you can't get your protected device underneath that, then you might look at the infrequent. But typical applications like substations and factories and things that are going to see a lot of faults, you're going to want to use the frequent fault if at all possible. Okay, so we have 2 curves here. Let's go back and talk about delta Wye transformers. When we're worrying about through faults and winding damage, we're worrying about the current through any one winding, primary or secondary. So we have to look at the highest current through any one winding for any particular fault. And we have to remember for a delta Wye transformer, our protected devices on the primary are not looking at the current through that actual winding. They're looking at this line current, which is the sum of these 2 currents, right? Whereas on the Y side, my relay, my CT, or my fuse, it's looking at the actual current through that winding. So at normal full load for my transformer, if this is a whatever kVA rating this is going to be, each one of these legs is going to be at full load. So under normal load conditions, 1 per unit. But if I have a fault, a line to ground fault on the secondary side, when I have full rated current through the faulted winding, I'm only going to have, or whatever this current is, my fault current, I'm only going to have 58% of that through the other primary side of this in terms of the transformer rating, right? Because the fault current's all flowing through this one winding. Current, remember, in a transformer, I can't have current flowing in this winding unless current's flowing in this winding. So I have fault current in this winding, I've got to have fault current in this one. So when I have my full current, let's say this is where the 1 is where my transformer damage curve is, I've only got 58% of that as seen from the primary side. So I have to adjust the damage curve. And we do that by plotting a second curve. And it's 58%, which is 1 over the square root of 3. So I plot a second curve. And I try to stay under this with my primary protection. But remember, this only applies to ground faults on the secondary of a delta Wye transformer. And it only applies for the primary protection. If I have a, let's say I don't have a main breaker here because this is a pulp mill, but if I had a main breaker down here and I had a fault downstream of the main breaker, line to ground fault, I don't have to worry about this curve. I can use this curve because this device is on the secondary side. This curve only applies for my primary device. Could be a fuse up here or a relay. So this is the plot unbalanced option here, the 58%. The 87% is for a different situation. That's for delta-delta, line-to-line faults on delta-delta transformers. But this is going to, if we have a delta Wye transformer, this is going to default to being on. If I were to go back to database, let's say I change this to a delta-delta. If I go back to coordination, then it changes, right? Now I've got the 87% curve, not the 58%. So again, that 58% curve only applies for delta Wye transformers. It's only for ground faults on the secondary side. And it's only for use in comparing the primary protection to that shifted curve for the damage protection. Okay. Not going to spend much time on this. This will be in the handout that we make available. This is just the National Electrical Code requirements for transformer overcurrent protection. Transformer inrush is only if we have to have our primary device be higher than this so the transformer doesn't trip when we first energize it on inrush. So we usually typically like 6 times, 8 times, or 10 times, something like that for 1/10 of a second. That's just a rule of thumb. There's nothing that says it has to be, always has to be less than that, but in general, that seems to work pretty well. But remember, it only applies to the primary. So you might see your secondary device down here. It doesn't matter because that's not going to see that inrush current, right? So this inrush point is only a concern from the side that you're energizing the transformer from, normally the high side. All right. Talk quickly about TCC clipping and tick marks. Yeah, it's kind of a source of confusion, I think, sometimes. We'll look at why we have those and why it's a good thing to use them. So let me go back. Let's look at a typical manufacturer's curve I get for, this is a 480 volt microVersaTrip Plus trip unit. So this curve, once I get on the instantaneous trip or the short time trip, it just keeps going, right? It doesn't matter. My manufacturer's curve goes on forever in terms of the magnitude of the current. So it doesn't provide us a lot of information about what the actual maximum fault current's going to be. Let me look at another example here. Here's a case where I have a primary fuse and a feeder breaker, and I have got basically the manufacturer's curve here. There's no clipping of this curve. I don't have any information about what the actual fault current is going to be. So it looks like this feeder breaker trip unit is not going to coordinate with this fuse, right, because they overlap. So this appears like an issue of miscoordination, perhaps. But I'd like to know, for a fault downstream of this breaker, what the maximum fault current is going to be. Because that's the highest I really need to worry about. So I can look at my short circuit currents and I get, 21,000 coming down this way. So that's really the most fault current I would really ever have to worry about. So what we can do in EasyPower is we have the concept of these tick marks. So I can come in here, if I go to the circuit breaker data, under the short circuit tab, down here I have TCC ticks for phase short circuit currents. I have three options: momentary, interrupting, or 30 cycle, depending on which short circuit network you want to use. So I'm going to pick the momentary. That's the highest value because I have instantaneous trip. So if I select that, then I see this little arrow down here. And again, if I hover over the arrow, it's going to tell me that this is for 2D1, which is this breaker. It's asymmetrical current, and it's 31,368. This is the highest possible current that this breaker can see in my system. I don't really have to worry about any of this part of the curve over here, because this breaker in this one line, in this system, can never see current above where this line is. So if I extend this line up, it's starting to look a little bit better, right? I can do the same thing for the fuse. I can put my tick marks in, okay? You can see that it's much higher because it's the maximum fault current, right? 12,777, but remember that's an amps at 1247, not 480. So in general, the default is to have these tick marks turned on in EasyPower. So every time you open the TCC, you're going to see these, and there's going to be one for each overcurrent device. Now, if I decide I don't want it, I can go back and turn it off like I did in the equipment data. I can also just highlight it and delete it in the EasyPower. Sometimes you're going to get a bunch of these on top of each other, and they'll overlap, and you need to rearrange them or delete some. So now I can see that I'm getting, this is much more likely, it looks like it's going to coordinate because this breaker simply cannot see current up in this region. So to go to the next step, why not just stop that curve at its maximum fault current? And that's the concept of clipping. Again, under the short circuit tab, we have TCC clipping, and I'm using momentary because it's instantaneous trip here, so I went to higher value. So that's one setting. That's the TCC clipping. If I change this to none, and it goes back and looks like it did before. So that's why we like to use the TCC clipping. It stops the curve at the maximum fault current that it can see. So we talked about this. Oh. Hang on. Coming back. Maybe. So in EasyPower, when you first create the TCC, it's going to have the TCC curves will be clipped by default. I believe they're all always clipped on using the momentary current. And there'll be a short circuit tick mark for each device. Again, you can turn those on or off. You can change them from half cycle to 30 cycle or 5 cycle. You can show all 3 tick marks. It's up to you. But that's why you see those, and that's the intent of why they're there. The other thing to remember is every time you open the TCC, or you create one anyway, it's going to fault every bus. And so the tick marks and the clipping always represent the maximum current through that device. But if I fault a single bus, the tick marks and the clipping can change. So just wanted to look at that real quick. If I just come down here, of course I can fault this bus just by double clicking on it. And if you watch the tick marks, they're going to move. So when I just fault one bus, my clipping is based on that fault, as are my tick marks. So this fuse curve stops at the maximum current it would see for this fault. So sometimes if you can't figure out why your curve has just disappeared, it may be because you have a single bus faulted. I can come back and do fault bus, and then it'll fault all the buses, and then I'll get the curve back. All right, I know we're running a little long. I got one more simple topic, I think. I call it last and least. The I2t is a function of on the short time delay on the 40-volt trip units and sometimes on the ground fault. Basically, it's cutting off the corner of the short time curve. So some confusion comes by the names that we use. But historically, we call it in or out. So in is on and out is off. And really, the main purpose of this is improve coordination with downstream devices that have some kind of I2t shape, which is primarily going to be fuses. So the problem is, in many cases, it's going to make your fault clearing time slower, which can increase the arc flash. So you can look at a quick example of this. We'll wrap up here in a short bit. So I kind of stacked the deck here a little bit, but here's a fuse down here on this motor starter. This is this guy, red guy, and then this is my short time trip on this GE breaker, Microversa Trip Plus, right? So right now, you can see down here the I2t delay is out, so it's off. This is the normal short time delay. It's just a constant delay above a certain pickup level, which is this value here. If I turn the I2t on, or in, basically I'm going at an angle. I'm cutting off that corner. So you can see if my fault current was in this range, it's getting slower, isn't it? With the I2t out, it's always going to be faster. So it would be preferable to just increase the short time pickup and leave the I2t out in most cases in terms of arc flash. So if the I2t is on, you may want to look and see if you can turn it off. If you don't have fuses downstream, there's really not a lot of benefit gained by using the I2t function. So sorry for running late. Not sure if you have questions. I think there's a way you can indicate that on your screen there, and I should be able to call on you. If not, feel free to email me, and I'll be glad to answer any questions that you have. You can always call tech support if you have particular issues with EasyPower or the program. And let us know if you have any other topics you would like to cover in webinars, and hopefully we'll be doing these on a more regular basis in the future, and look forward to talking to you again. Maybe we'll see some of you in Kansas City next week or one of the future training classes. We've got one coming up in Portland in July as well. So I'm not seeing any particular questions. Oh, is there one? Okay, got a question here. Okay, Mike Brindle, question.
Yes, David, in your earlier, one of your early examples where you were showing the, I think it's the short circuit table and the different breaker ratings,
right,
for power circuit breaker versus multi-case breaker.
Yep.
Now, could you bring up a interrupting report for that same situation? I guess I have a little bit of question on, I've been seeing differences between the two reports and don't quite understand why they're different.
So the difference, the main difference is going to be that for the short circuit report, like we looked at,
yes,
that's the bus fault current. That's the total fault current at the bus.
Okay.
And when we do the equipment duty report, it actually computes the current through each breaker individually. So it's going to subtract out any fault motor contribution coming back up the other way. So actually, if you looked at a bus, let's say you had 6 breakers.
Right. You
look at the equipment duty report, the fault current, the duty current for each one of those breakers can be different because it's taking into account the contributions that might be coming back up in the other direction.
Oh, okay.
Does that make sense?
Right. Yeah, it does.
Yeah, it can be a little confusing to try to compare the two.
Yeah, in general, I've always used the interrupting report.
And that's more, yeah, and that's going to be more accurate because of the smart duty. That's what we call the smart duty function.
Sure. And, of course, it'll flag my one line for
yeah, you'll turn red.
And devices or, devices that are beyond the threshold.
Right. So in the short circuit report, it's more of a, kind of a general value for comparison purposes. If you were adding devices in the future, it just gives you a comparison point. It's always more accurate to do the equipment duty report.
Okay. And then, of course, going along with that equipment, the fault or the current in the equipment duty report would be, just correspond directly one-to-one to the device you're using.
Exactly. So it's going to be specific to that breaker. It's a more accurate analysis.
Sure.
It's it's especially important if you have generators on your system and that kind of thing. So.
Yes, which I usually do. So. Okay.
Does that answer your question?
Yes.
Okay.
Thank you.
Great. Anybody else? Questions? Oh, see one? No. There's Mike. Well, I'm not seeing any questions, and I apologize for running late. I always seems to run longer than I expect. But anyway, I thank you all, and if you have questions, feel free to email me, and hopefully we'll run into you at some training or some other situation. So thanks everybody, and have a great day.